We are recording. This is pinned. This is shared. This is almost on. Merry Christmas, by the way, everybody. Um, yeah, show that if P is prime, the only solutions to x squared congruent to 1 mod P are integers x such that x is congruent to 1 mod P or x congruent to -1 mod P. Okay, this is what I would consider an easy problem. Okay, so you might read this and not feel that it's easy, but it turns out that it's really, there's almost nothing to do. Okay. So let's just take a look at this. I don't know if you've tried it. I don't know if you've done it. So there's I often get messages which are of the form, I can't do the problem. I look at the solutions that it helps, but you have to be very careful about the amount of time you spend on a problem before you go and check out the solutions. It's tempting to always go and take a look, but and I don't have like a general strategy because it's very personal, individual. But I one thing I would suggest is try to resist a little bit more before you go take a look at the solutions when you're stuck. Um, it gives you a false impression of understanding when you see how it's done. So you have to see some solve problems, but if that's the only thing you see, it's doesn't really train you to solve problems. Okay, so we're given here that x squared is congruent to 1 mod p. And we'd like to conclude something from that. Now, this thing is squared, so it's not going to be the Chinese remainder theorem or anything like that, or it doesn't seem like it's going to be anything like a straightforward application of that. But what do I see when I see x squared congruent to 1 mod p? And I want to conclude that x is congruent to 1 or -1. I mean, if you think in terms of equality, it sort of rings a bell, maybe. And the thing is just the following. This the only thing that you have to do is to see that this means that p divides x squared -1, right? To a and b are congruent mod p when p divides their difference. Okay. Now, the minute you write it this way, hopefully the problem is over. Okay. Because there are two things here. You see x squared -1, and I'm guessing it's almost automatic that you see x -1 times x plus 1. Okay. So this first step is like almost immediate. So p divides x -1 times x plus 1. And the other thing that should become automatic, hopefully in the next few days, is that when you see a prime dividing a product, you know that the prime must divide one of the factors. Okay, so p is prime implies that p divides x -1 or p divides x plus 1, and then you can see that I'll just write etc. here because the rest is just reapplying the definition. Okay, one more step. Okay, so that's it. Okay, so that's number 17 on page 285. If you had done it, That's great. I didn't go look at the solution. I don't know what they say there, but I suppose that's basically what they're doing. I don't see another simpler way of doing this. Questions, suggestions before I move on? I'm missing a window. That's better. Here's one. And where's the chat? There's the chat. Very good. Nothing there. Okay. So next. This is sort of I'll skip that one for now. I wanted to do number 21, but it's just like it's a bit boring. Let me show you number 51 because that's something I didn't really discuss very much, and it's kind of cool. It's very easy. Number 51 is like super easy. 51, 52 actually that I'm going to do. 51 and number 52. I don't know if I had put 52 in the list. If not, I'm adding it right now, right this minute, because it's a cool question. I don't know if what 4.4. No, I didn't put it there, but I'm adding. I decree that number 52 is added to the list right then and there. So 51 is express each non-negative integer a less than 15 as a pair a mod 3, a mod 5. Okay, so what do they mean by this? Okay, so what I'm going to do, I'm just going to write down the numbers from 0 to 14. Okay, and we're going to reduce those mod 3 and mod 5. Okay, and we get a pair of sequences. All right, so this will be mod 3 and this will be mod 5. Okay, so 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2, right? Mod 5, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. Okay. Now, what does the Chinese remainder theorem tell you? It says that if you take any pair in this list, okay, in these two, the bottom two lists, okay, you take any pair, then there is a unique number mod 3 times 5 congruent to both of those, okay? So essentially what the Chinese remainder theorem tells you is that if you look at those pairs at the bottom, I mean, like for example, the pair 1, 4, it appears exactly once. And if you look at all the pairs, that's the only one, right? So Chinese remainder theorem says each pair, like 1, 4 that I've circled, appears once, oh, come on. Once and only once. Okay, so that's a consequence of the Chinese remainder theorem. right? So congruent to let's say I mod 3 and congruent to j mod 5. 3 and 5 are relatively prime. So there is a unique solution, mod 3 times 5, which is 15. Okay, and this is something that keeps coming back in all, I mean, in everything we've been doing, and I'm going to show you other examples later, which are sort of practical. So these pairs appear exactly once in that list. So it means that once you look at a pair, you know that you've got one of those numbers between 0 and 14. Okay, so these are the pairs that they're asking for. There they are. So it's not like the deepest or hardest question, right? 52 is interesting though. So here's 52. And this is a good example. It says, explain how to use the pairs found in exercise 51 to add 4 and 7. So adding 4 and 7 using the pairs from 51. Okay, so again, to give you, I mean, these are very small numbers, but again, keep in mind that rather than having 15, it could be like this humongous number, and we could have more than just two primes. We could have several primes multiplied together that give us a humongous number. And rather than look at the big numbers here represented by 0 to 14, we could look at their remainders mod these smaller primes represented here by the pairs. You see all the numbers are less than 4, right? So can I add big numbers looking at only the smaller ones? Yes, here's how it works, okay? So you look at the pair that corresponds to 4, it's the pair 1, 4, okay? The pair corresponding to 7 is the pair 1, 2, right? If you look at, there it is. Okay, so let's say I want to add 4 and 7. I'm just looking at the pairs, okay? So this is what happens mod 3. This is what happens mod 5, okay? If I add those, I'm going to get, yes, I'm going to get 2, and here I'm going to get 6. But I'm looking at things mod 5, so this is the same as 1, mod 5. This is same as 2, mod 3. So I've got the pair 2, 1. Let's look it up. There it is, corresponding to 11. As expected, 4 plus 7 is indeed 11. So you see that you can actually work with the pairs and you get the right result. And this is the consequence of what we said, that if A and B are congruent and C and D are congruent, then when you add them up, you get the same thing, you get the right thing. And the Chinese remainder theorem also. So there's a lot of things happening here, okay? This is a good example to illustrate many things that we've looked at, okay? Questions on this?
No, pretty clear.
All right, good. Gonna move on to number 55, which is also pretty cool, different, very cool. Okay, let's go to 55. 55. Okay, 55. Find the discrete logarithms of 5 and 6 to the base 2 modulo 19. Find the discrete. So I didn't spend much time on this, so I will forgive you if you don't remember what this means. So I will refresh your memory. Find the discrete logarithms of 5 and 6 base 2 to the base 2. modulo 19. Okay, so recall. I have a prime which is 19. Here P is 19, that's a prime. I know that Z19 has a primitive root. What is a primitive root? It is a generator. We don't know which it is. Here we're told that 2 is a primitive root. Here it's 2. What does that mean? It means every A in Z19, which is not 0, is of the form a power of 2. Okay, so if you look at all the powers of 2, you will, mod 19, you will generate every number between 1 and 18. Okay, so what is the logarithm? Is you're looking for the exponent. Okay, so the discrete discrete logarithm of 5 is the value of E if 5 equals 2 power E mod 19. Okay, so and keep in mind, this is important, that it is believed to be difficult to find this value. Okay, so if you keep that in mind and you're asked to compute the discrete logarithm, then you will not be trying to remember a shortcut to find it. There is no known shortcut, which means, what do? You take powers of 2 until you hit 5. That's basically it. Okay, so no shortcut. I'll just state it like that. So compute powers of 2 until you hit 5 and 6. Right, we're asked for 5 and 6. Okay, so let's do that. So I'm working mod 19. Okay, so 2 to the power 1, that's 2. 2 power 2 is 4. 2 power 3 is 8. 2 power 4 is 16. Then I'm going to move on to 32, but I'm really lazy, so I'm going to see this as, so 19 minus 3 is 16. So this is the same as minus 3. So 2 per power 5 will be 2 times minus 3, which is minus 6. 19 minus 6 is 13, right? So what I did, I'll just write it here. Is that 2 times minus 3 equals minus 6. 19 minus 6 is 13. So that's how I got my 13. 2 power 6. 2 times 13, there's really no faster way, I think. I don't see it anyway. So 2 times 13 is 26, which is 7 mod 19. Is that correct? You don't want to mess up, because then it's just domino effect. Everything after that is crap. But I think this is correct. 2 power 7. 2 times 7 is 14. You see how chaotic this thing is, right? You see how we're going all over the place. It's very interesting. It's quite puzzling. 2 power 8. 2 times 14 is 28. So that would be 9 mod 19. Okay. 2 power 9. 2 times 9 is 18. Notice this is minus 1. And that also basically tells us that we're good, that 2 is indeed a primitive root, because you better hit minus 1 at the halfway point. If you hit, I mean, there's stuff you don't know here, but if you don't hit minus 1 here, you'll be hitting 1 either here or before, and you don't have a primitive root. But anyway, so 2 power 10, that's minus 2, so that's 17. 2 power 11 will be 2 times, well, that's minus 2. 2 times minus 2 is minus 4. 19 minus 4 is 15. 2 power 12. That's 30. 30 mod 19 is 11. I didn't say this was like super exciting, but it's interesting. I feel like Mr. Spock. 2 times 11 is 22, which is 3. 2 times 3 is 6. We got our 6. 2 power 15, that'll be 2 times 6, 12. 2 power 16, 2 times 12, 24, which is 5. We got our 5. 2 power 17 is 10. 2 power 18. And now at this point, you double check that you've done everything right, because if you've done everything right, 2 to the power 18 by Fermat's little theorem, this is 2 to the p minus 1, it should give you 1. So what is this? This is 20, right? And 20 mod 19 is 1. This is the good, as expected. You're supposed, if you don't get 1 here, it means you messed up somewhere, okay? Okay, so the answer to the problem, so the discrete log of 5 in base 2 is 16, and the discrete log of 6 is 14. These are the exponents. This is base 2 mod 19. Okay. This is really not very difficult. I mean, this is just, you have to know the definitions, and you have to keep in mind a few little basic tricks, which means essentially that if you do enough problems, it should imprint for a little while anyway, long enough, and then it goes away, but that's fine. Okay. I don't have a very good memory. I don't know if it's my fault. I don't know if it's because I don't practice it enough. I have colleagues. I have a Russian colleague who works in Great Britain, and this guy has just an indecent memory. It's just, we're talking, and then we sort of both remember, oh yeah, we're working on something. Oh yeah, this is true because of this theorem. And I'm going, I don't remember where it is. He says, yeah, that's in this paper. It's on the second page, top right. And just like, when's the last time you looked at that paper? I said, 10 years ago. So, come on. Just like, yeah. So I don't have that kind of memory. Next. That was 55. So you can do 57. 57 is a sign I'm not going to do it. Let's move on. Unless there are other questions for 4.6, I'm 4.4. He's just showing off at that point. Yeah, it looks like that. The way I told the story, it looks like he's showing. Yeah, maybe he is a little bit, but he's right. So yeah. No, he's got a good memory. Which is like super useful if you happen to have that. It's great. It's very efficient. Yeah, so 4.4, going once, going twice. We're going to 4.6. 4.6. Okay. Yeah, okay, so I started doing this problem, which is like a super good problem, because if you can do that, you can just, you've understood RSA. So it's number 27. And I spent a little time on it, and I don't know if I'm going to do all the details here, because I'm just going to put you even more to sleep than I'm already putting you to sleep. You see, I was in the kitchen doing the problem, and I was lazy. No, I'm sort of joking, but I wanted to do it with basically the calculator on my phone, which is not the best calculator, but like the basic calculator on my phone. And I did it. I managed it just by hand and with my little baby calculator. Okay, so basically, no, I gave it to my daughter. I don't have that little baby calculator anymore. But you know, the basic calculator on a phone. It adds, it multiplies, it divides. That's it, right? So I did this problem only with that. So it's possible. So how do you do it? And no, I'm not showing off. It's just what I want to explain is how you can actually do that, right? That's the point. So here's the problem, number 27. This is on page 305. So what is the original message encrypted? So message encrypted using RSA with n equals 43 times 59 and e equals 13. I think these values keep coming back. And the message is 0667 1947 0671. So decrypted. Basically, that's it. Okay. So, I mean, I'm saying that if you can do this, you've understood the whole thing about RSA. Not, I mean, there's little bits and pieces missing, but still, okay. So n here. So I'm going to review a few things about RSA as I'm doing the problem. So n is 43 times 59. These are primes P and Q. Now, of course, in real RSA, you don't take these little baby primes. You take humongously big primes. That's the point. Oh, by the way, if you look at that video, you have to go and see that video. I should have written it down, but there's actually like a $75,000 prize if you can factor a certain n, and it's given in the slides. So it's the product of two primes. If you find the prime, 75,000 bucks. So that's hard. That's how hard it is. So if you want to make quick money, that's not the way to do it. Okay, so this is n. These are two primes, P and Q, and this happens to be 20. What are you? 2537. right? Which is slightly bigger than 2525. So what? It means that our blocks have length 4, right? If you remember, and letters have two symbols, 2 digits. Okay, so it means that the message here has 6 letters. There are 6 letters that are encoded, 2 letters per block. Okay, so what do we need to do? We need an inverse of 13 mod 2436 mod p minus 1 q minus 1. Okay, which is this is 42 times 58, which is 2436. 2436. Okay, that's how RSA works. Okay, and what we're going to do with this inverse is we're going to take each block, raise it to that power, and that's the way we're going to decode. Okay, to decrypt. Okay, so this part about the inverse, this is something that if I'm the bank, I've already pre-computed, obviously. Okay, but here we have to do it. Okay, so how do I find an inverse mod 2436? If you remember how this works, right? So how, I will skip a few details here, but it's doable by hand, right? So you use Euclidean algorithm, and you backtrack. Okay, so this is what I did. 2436 divided by 20. Come on, brain. 2436 divided by 13. That's 187 times 13 plus 5. You repeat. 13 is 2 times 5 plus 3. Repeat. 5 is 1 times 3 plus 2. Repeat. 3. This is unfortunate, but that's the way it is. That's how the numbers fell. 1 times 2 plus 1. We've got our 1 expressed as a combination of 3 and 2. Work back up. And you will find, so some work here, obviously. You will find that 1 is equal to, here, did I write it out? This is crap. 5 times plus 2, that's 937. Okay, I got it. 937 times 13 plus minus 5 times 2436. Okay, so by backtracking, you will find this. Okay, so this is your inverse. This is it. That's 937. Okay. So what do we do with that? So I'm going to take the first block. And when I said I did the whole thing, I didn't say I did the whole thing. I did the whole thing just with my hands and my little calculator, but I did only the first block. I didn't do all 3 blocks, I have to say. But a lot of the work that I invested in the first block would help me go fast for the second and third blocks too. But I did only the first block. Okay, so here we go. So to decrypt, the first block. So it is 0667 power 937 mod P times Q 43 times 59. And yes, I did that with paper. I really didn't need the calculator. It was just a little faster, but so how do you do that? Okay, there are a couple of ways. I'm not sure which one is faster. I think the way I did it is faster. So how do we do the computation by hand? I understand the point. The point is not to become experts at doing baby RSA by hand. That's not the point. The point is all the theory behind all the tricks. I mean, these are useful also when you have extremely large numbers to reduce the number of computations to do, right? So here's how I did this. So I have to compute 667 to the power 937, all this mod 43 times 59. Okay, this is what I need to compute. Now, method one is just repeated squaring, right? And reduce each time. Okay, and I've discussed this before. So what you would do is basically you look at 937, you write it in binary, and you use repeated squaring, which is a fundamental technique, by the way, to go faster. And I will use that, but I'm not going to work mod 43 times 59. I am going to work with smaller numbers. There's a little price to pay at the end, but it turns out it's not so bad. Okay, so method two, I'm going to work mod 43 and mod 59. Okay, so do you see what the theorem I'm going to be using at the end will be?
Chinese remainder?
Correct, right? So I've got two primes, 43 and 59. So I'm going to work mod 43, and then I'm going to work mod 59, which is much smaller. And in the end, I'm going to get two values, one mod 43, one mod 59. Chinese remainder theorem says there is only one number, mod 43 times 59, that does this. So that's the number I'm looking for, okay? So I will have to work a little extra to find it, but my computations have been much simpler. It seems to me. I mean, maybe I didn't try it. I didn't try repeated squaring and reducing directly, but I wanted to try it out, mod 43, mod 59. And so I'm sort of illustrating here. So this is, so here are some highlights of this exciting highlights of this. Okay, so I've got 667 power 937, and I want to reduce this mod 43. What am I going to use to do that? Which theorem am I going to invoke? Everybody together.
Wouldn't you just use the repeated squaring?
But I
To
can
make
go,
that simpler?
but I will, but I can reduce things quite a bit drastically before.
Fermat's little theorem.
Yes, Fermat's little theorem, right? This is a prime, P. So I can reduce numbers now using, so Fermat's little theorem, Santa's little helper. Fermat's little theorem says that a to the p minus 1 is congruent to 1 mod p if P doesn't divide A. So I have to check that P doesn't divide 667. It doesn't. We're lucky. Okay. But in fact, I can reduce 667 mod 43 immediately. Okay. So first step, I'm going to reduce 667 mod 43. Okay. What did I get? So now you just need a calculator, or do it by hand if you enjoy that kind of thing. Why? What area? Is it 18? Is that it? I think it is. Sorry. Okay, so 667 divided by 43 minus 15 times 43 is 22. Yeah. Okay, I see it. Okay, so 667 is congruent to 22 mod 43. So 667 to the power 937 is congruent to 22 to the power 937 mod 43. That's the first step, okay? So we've got much smaller numbers. Then I'm going to use Fermat's little theorem. Okay, right here. So 937 is equal to 20. Did I do the, what did I do? No. Yes. No. Did I? Wait. No, okay. Yes, sorry. There's a lot of numbers going around here and my sheet is not. Okay, so this is 22 times 42 plus 13. Okay, I want P minus 1 involved in the exponent. Okay, so 937 is 22 times 42 plus 13. Let me do just this piece slowly. So it means that 22 to the 937 is the same as 22 to the 42 to the 22 times 22 to the 13 mod 43, right? And Fermat's little theorem says this is 1. This is gone. Okay, so this is 22 to the 13 mod 43. Right? So because of the P minus 1 here, 22 to the P minus 1, that's gone. It's 1. I can just get rid of it. So my 667 to the 937, when I'm looking at it, mod 43 is just 22 power 13, right? And I didn't need to do anything very complicated to get to that. Okay. Now I used repeated squaring on that one. Now notice that 22 squared is, you can do the computation, but there's a little trick because 22 is half of 44. And I think you can, I'm sorry, I'm rambling. In the old days, I remember. 22 squared is 11. Which I think is easy to see, but anyway, I just computed it. Okay, so with that, and repeat, reduce, and we get that finally 667 to the power 937 is congruent to, what do we get? 2 mod 43. Okay, so you don't need anything very, very complicated for this. It's just, that's the only painful part. It's this repeated squaring and reducing. Again, I didn't try it with mod n. I don't know how fast it goes. But to illustrate the Chinese remainder theorem, this is a good example. Okay, next. My goodness. Same approach. Mod 59, and we shall obtain that 667 to the power 937 is congruent to, if anybody wants me to do more details for what I'm going to write, just say so right now and I will do it. I'm willing to do them. This is 38 mod 59. Everybody's gone to have a nap. Okay, so I've got my two values, mod 43, mod 59. Now I need to compute the value that the Chinese remainder theorem guarantees. Okay, so now we want the unique value mod 43 times 59 satisfying this, or these I should say, to make. Okay, Chinese remainder theorem. Okay, now if you look at the method that we found with that in the proof of the Chinese remainder theorem, it sort of makes a lot of sense when you have at least three equations. When you have two equations, it might not be so clear, but actually it's kind of cool with two values. So what I will need is, so we need to find the inverse of 43 mod 59, and we also need to find the inverse of 59 mod 43. We need both. Okay, now it looks like we might have to do two computations, but actually we just need one. All you need is to find those A and B that give you a linear combination that give you one from, and then you'll have both inverses at the same time. So this is just a single computation. It's a Euclidean, good old Euclidean algorithm. I mean, think about it. I mean, it's just the three key points in RSA, which is something like really fundamental in with modern technology. The three fundamental ingredients are the Euclidean algorithm, which is 23 centuries old, the Chinese remainder theorem, which is just about as old, and like the recent result is Fermat's little theorem, which is from the 17th, 18th century, right? That's so you never know. Okay, Euclidean algorithm plus backtrack. So you'll find 59 is 1 times 43 plus 60, I guess. Yeah. And then 43 is 2 times 16 plus 11. And 16 is 1 times 11 plus 5. Oh, that's... ugh. 11 is 2 times 5 plus 1. Then you backtrack and you will find that 1 is 11 times 43 plus minus 8 times 59. Okay. And so it means the inverse of 43. So the inverse of 43 mod 59 is 11. And the inverse of 59 mod 43. I wrote it as minus, but it's minus 8, right? You can, okay. And so now, if I go back to what I need, the solution, the number that I want is the following. Do I have enough room here? Yes. So the number I'm looking for is n equals 2. So mod 43, it's 2. So it's 2 times, okay, don't read this immediately. I think this is correct. Plus 38. 38 is what I need mod 59. So it'll be 11 times 43. I think this is it. I think this is correct, right? If I reduce, so look at this number n. Reduce it mod 59. The left-hand part dies. 11 times 43 is 1. So you get 38, which is what we want. Yes. Now, if you reduce it mod 43, the right-hand side is gone. Minus 8 times 59 will be 1. So you're left with 2, and that's exactly what we want. Okay. And this is, if you compute this thing, mod 43 times 59, you will get 1808 mod hello brain 43 times 59. Okay, this is, I just divided and looked at the remainder. Okay. And so if you look at the letters now, let's write the letters like this. A, B, C, D, E, F, G, H, I, L, M, N, O, P, Q, R, S. This is 0, 1, 2, 3, 4, 5, 6, 7, 8. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So this is S, I. These are the first 2 letters. And it's the same thing for the 2 other blocks. So I'll leave those to you to have fun with. Okay, but it's sort of fun. I mean, it's not like super fun listening to me explain it. I think it's much better if you do it yourself, I think. Right? It's really not that bad. It's really not that bad. I went a little fast at the end there. I had no one to stop me. So any questions about this?
Where's the 38 coming from?
Where did what come from? 38? This
Yeah.
one? This guy?
Okay. Yes. Okay, sorry.
Yeah. Yeah, I should. Other questions? Okay, that's all I had prepared as problems go, because again, I don't want to do them all. Well, that's enough. You have to do some. There's the WebWorks, and the more problems you do, the more these theorems will sort of imprint, right? Fermat's little theorem, Chinese remainder theorem, Euclidean algorithm. These are like the big important ones, obviously. That okay? That good? Was that good for you?
Yeah, I just had one question for
Yes.
for the two other blocks. So we would do the same computation to find the let's say the 2 mod 33 and the 38 mod 59, but
Yeah.
with the other blocks, and then use the same inverses of 11 and -8, right?
Let me see.
So let's say
Yeah,
in your
yeah.
n equals 2 times -8, blah, blah, blah. The only two numbers that are going to change is 2 and 38.
Correct. Yes, we've done. Yeah, you're right. We've done a lot of the work. Actually, the next blocks will be much faster.
Okay,
Yes.
perfect.
Good point. Yeah. Yeah, it's only so the 937, we've already reduced it, mod. Yeah, we already know the exponent. So yeah, there's a lot of work that we've done for that first block. We can reuse a lot of stuff for the next
That
two
is
blocks.
if we continue to use method 2 for the two other ones.
Yes. Yeah. I should try the first method from the start just to see what happens. I don't know how it's. I didn't find it as interesting, so I didn't want to do it. It's just like just repeating, repeating squaring, just calculator is like that. So I did it this way. I thought it was more interesting, more illustrative also, but it's arguably simpler to do it just by repeated squaring right from the start. It's simpler, but yeah. Either way. Other questions?
On the test for like, can we use our calculator to help us with things like the Euclidean algorithm?
Yes. Yeah. 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 Yes. Obviously.
Okay.
Yeah. So you have the WebWorks. I think it closes maybe Monday, Tuesday. I don't remember when. Monday. And I'll be around if you have questions, obviously. Until then, I will be. I might not answer your Mio just like in the next 5 minutes because it's the weekend, but I will be paying attention and responding as soon as I can. Okay.
Thank you.
All right. See you. Have a good weekend.
Have a nice
Bye-bye.
weekend.
Thank you.
Thanks.
Thank you, sir.
Bye, thank you.